So we will start today chapter 2 with the first lesson on solving systems of linear equations by the method of elimination and some brief discussions on the method of substitution that some of you use when you solve systems of linear equations. This will be a major topic because, as you already know from previous lessons, there are lots of important practical applications that lead to linear equations. You could do, in fact, quite a lot, far more than what we could do with just two linear equations with two unknowns, for which we can illustrate the concepts by drawing lines, like we did last time. We can actually deal with lots of unknowns, far more than just two, and we could do pretty interesting applications in economics using linear equations. So remember, finite mathematics is essentially an incursion on some basic topics that hopefully are interesting to you because they are related to real-life applications. And for the most part, for a good portion of the course, all of these tools lead to linear equations of some sort or linear inequalities. So in order to be efficient with tools like this, we need to build efficient methods. So for the class today, I'm going to start with some familiar things like solving a 2x2 system with the method of elimination, but I really want to focus on the main goal. I should say the additional goal is, to me, is the main one besides just knowing how to solve the equations, but namely understanding that the method of elimination, it's the advantageous one. And once we understand why this is advantageous to use, then you would understand why mathematicians develop fancier methods to apply this method for larger systems. Because the goal is to essentially use some interesting algorithms that will basically make use of elimination in a smart way so we can solve larger systems than just 2x2. For the 2x2 case, maybe not big of a difference between substitution or elimination, but you will see elimination is still more efficient often. So let's just start right away with an example. Let's say I want to solve a 2x2 system. And we already did that in some previous context, but let's focus on the math for now. So the first equation is x plus y equals 5. The second one is 2x minus 3 equals minus 8. So the thing to understand with the method of elimination is that one needs to multiply one or sometimes both equations so that by adding the two, we can eliminate one unknown. So the idea is to multiply one, or sometimes, as you will see in the next example, or both equations, one or both equations, with convenient coefficients or with appropriate coefficients, such that by adding the equations, one unknown is eliminated. And you get to choose which one to eliminate. And notice I mentioned this time by adding, and there's a subtle reason for that, because sometimes you will say, well, we have x plus in both equations, so why don't we subtract the two? And then, that means you will eliminate x. And that is correct, but because we will build an algorithm, and algorithms are efficient if we have very clear defined steps, I want you to think in terms of adding the two. So that means we will need to have the coefficients of opposite signs and equal. The coefficients of the unknown to eliminate should be equal and with opposite signs, so that we have this kind of standardization of the method. Once I multiply by those appropriate coefficients, when I add the two, then the unknown is eliminated. Now notice sometimes there is a free lunch, very rarely in life and also rare in math. But by free lunch, I mean, I could multiply, for instance, the first equation here by minus 2. So I could do that if I want to. So I can eliminate x, but it's far easier to just add the two, because it so happens that y already has opposite coefficients. So by simply adding the two, I can eliminate y, and that gives me x equals minus 1. Then the last step is a substitution. I mean, it's kind of like I lied to you, right? Because we said that we don't use substitution, but that's a much easier substitution because once you find one unknown, the other one is immediately solvable, right? So you plug in minus 1 for x, let's say, in the first equation. You can choose either of the two equations, and then you can solve for y, which in this case gives you y equals 2. So the solution of the system is minus 1 and 2. You will see actually that we can find efficient methods so that even this substitution step at the end, it's actually much more efficient than what I just showed you. Again, in the 2x2 case, it doesn't matter as much, right? Once you eliminate one unknown, you're practically one step away from finding the other unknown. I did mention here that sometimes we need to multiply both equations by a convenient coefficient. So take a look at when that needs to be done. So let's take a look at a different example. So let's call this example 1, and let's move on to example 2. So the first equation, let's say, is 2x minus 3y equals 3. And the second equation is 3x plus 2y equals 11. Obviously, if we just add the two, nothing changes. I mean, there's no elimination. And also notice that we can just multiply one unknown by something so that we can get the opposite sign of the coefficients. So you have to make up your mind which variable you need to eliminate. It's up to you which one you pick. Let's say I want to eliminate x, which means I need to multiply both equations by some convenient coefficients so that they are of equal and opposite signs. So there's no rule on how to do that. You just take a look. We have 2 and 3. Obviously, if we multiply, let's say, the first equation by 3 and the second one by minus 2, that accomplishes the task of coming up with opposite coefficients. Alternatively, you could say minus 3 for the first one and 2 for the second. Same idea. The coefficients of x should be equal in absolute value, right? So they should be opposite, equal but with opposite sign. Don't forget, that's another very important habit to form early on. When I say you multiply an equation, remember that means you multiply really the entire equation. If you rush, sometimes you forget to multiply both sides of the equations, and that, of course, leads to mistakes. So I multiply by 3 everywhere in the first equation. That's 6x minus 9y equals 9. Minus 2 times the second equation, that gives me minus 6x minus 4y equals minus 22. I like to sometimes draw a line like that. You can just say in your mind that I'm going to add the two. Here I wrote add so that you guys follow what I'm talking about. Later on, we just do it faster. 6x minus 6x is 0. That was the goal. Minus 9 minus 4, that's minus 13y. 9 minus 22 is another minus 13. Divide by minus 13, and that gives me y equals 1. Again, the last step could be a quick substitution. Let's go back to the first equation. Replace y with 1. That gives me 2x equals 6 or x equals 3. And 1 and 3 is the solution of the system. Now, here's how substitution would go. So how substitution looks like as a method if I use it for these two examples. In the first example, it's not big of a deal, but it's still probably not that not as efficient as elimination, right? So first of all, which one do you substitute for the other, right? So substitution as a method means you pick one variable and you solve in terms of the others, and you substitute it in the second equation. Obviously, the easiest thing is to choose to solve for x in the first equation. So x equals 5 minus 3y. And then you're going to bring it into the second equation, not forgetting to use parentheses appropriately. And then you have to expand, do the work. So minus 9y would be minus 8 minus 10, which is minus 18. And then finally, if I divide by minus 9, I get y equals 2 as expected. Not much of a difference, but you should still realize that it's already a little tad more tedious. Which is the reason why, again, I mentioned this already, from this point on, you're basically required to use elimination. Even though the section so far doesn't say use elimination, I'll ask you to do just that, because later on it's essentially elimination, but in fancier forms if you want. So elimination is the way to go for linear equations. But if you're not convinced why this is so tedious, let's see how it looks like if I use substitution for example number 2. There are no good choices here if you look at the second example on how to choose the variable to solve for. You're going to deal with fractions, right? So let's say I'm going to, again, choose x in terms of y. 2x equals 3y plus 3. Then x is going to be 3y plus 3 over 2. Then you're going to substitute this in the second equation. So that's going to be 3 times 3y plus 3 over 2 plus 2y. And I'm too lazy to finish this. You can do it for practice if you want. You should get the same answer as before. But I hope you guys are convinced that this is rather tedious. And this is so. Before we talk about systems of 3 equations and 3 unknowns, and by the way, just to give you a preview of coming attractions, we will in fact be able later to solve a generic linear system. That is a system of m equations and n unknowns. In other words, it doesn't have to be the same number of equations and unknowns. So the algorithm is quite powerful, and it will give you not only the solution, but also a situation when the solution doesn't exist. So there is also terminology that we should mention here, and I'll talk about more with an example. We have basically 3 possibilities when it comes to linear systems. So basically a linear system can have no solutions, in which case we call it inconsistent. It could have a unique solution, or infinitely many solutions. And the good news is that the method of elimination, the more sophisticated way of using elimination, which in the next section is called the Gaussian elimination, the same algorithm basically gives you the answer no matter in which case you are in. So no solution, unique solution, or infinitely many solutions, you will be able to determine that using the same process. For now, let's just use essentially our judgment on how to proceed with the elimination. So we'll not talk about the algorithm right now. That's the topic for the next section. So let's see, the count is example 3. Let's, like I said, let's take a system of 3 equations and 3 unknowns. So that's 2x minus 3y minus z equals 0, and 3x plus 2y plus 2z equals 2, x plus 5y plus 3z equals 2. So when it comes to elimination here, it should be obvious that we need to do a 2-step process. Basically, we need to eliminate one variable by pairing 2 equations. So the goal is to eliminate one variable from all 3 essentially. So you decide to eliminate z, let's say, from all the equations, then you have to pair 2 equations and eliminate z from both of them. So the goal is to basically, once you eliminate one equation, one unknown, is to obtain a 2-by-2 system, which can be solved again by elimination. So the more variables, the more elimination you have to do. So I decide to choose z to be eliminated. And again, the choice of which variable you choose to eliminate has to do with some convenience of coefficients. If you look carefully, let's say let's say I want to eliminate y, right? If you look at the system here, that's not convenient because I'll have to deal with lots of coefficients to multiply. I'll have to multiply, for example, the first by 2, the second by 3, then we add. It seems that 1 or minus 1 is very convenient as a coefficient because then I can multiply it by the opposite of the coefficient that I want to eliminate in the other equation. So for example, if I want to eliminate z, that's a good choice, or x, that's also a good choice. Let's focus on z, for example. So how do I eliminate z? Well, if I take the two equations, the first two equations, I can multiply the first equation by 2, and that creates opposite signs for the coefficients of z. So the coefficient of z becomes opposite to each other. So I can take the first two equations. First one multiply by 2, as I said before, so 4x minus 6y minus 2z equals 0. The second equation is the same. And then we just add the 2 like before. Plus 0. And I'm going to save this for later, this equation. That's an equation in x and y. Now I have to use another pair of two equations. I could use the first and the second. Excuse me, I used that already, right? I could use the first and the third, the second and the third to eliminate z. Again, the first and the third is the most convenient one because I don't have to multiply two coefficients. If I chose 2 and 3, the second and the third, I'll have to multiply again this one by minus 3, let's say, and this one by the third one by 2 to make the signs opposite. As it is, like I said, the best thing to do is to still use the first equation and just multiply it by 3 this time and pair it with the third one. So the first equation times 3 becomes 6x minus 9y minus 3z equals 0. And the last equation, I copy it, x plus 5y plus 3z equals 2. Add the 2 just like before, 7x minus 4y plus 0 equals 2. Okay, together these two form a 2 by 2 system, which I'm going to copy it again here. Let's see. I want to check something first before I move on. Okay. 7x minus 4y equals 2. 7x minus 4y equals 2. Making a pause here because I want to check something before I move on. Okay, so this basically has infinitely many solutions. Because the second equation essentially is the same. Yeah, I made this pause because I think I wrote something different in my notes, but that's fine. So 7x minus 4 equals 2, the second equation is the same, which means if I were to do elimination again, we're not going to get a specific value for x. Now, obviously, there are infinitely many possibilities for x and y. So obviously, the system is consistent, but you don't have any unique solution, right? You have infinitely many solutions. If you were to continue with the elimination, you will end up with 0 equals 0. So for example, if I multiply the first one by minus 1 to try to eliminate x or y, and you add the two, you get basically a true statement no matter what x and y is. In practice, what we do if we want to show what a solution is, we typically solve one in terms of the other. So we could say, for example, that if I solve for x, move 4y on the right-hand side, that's x equals 4y plus 2 over 7. And you could just say that y can be any number. So y is arbitrary. But basically, if you do the elimination until the end, and you end up with 0 equals 0, that's essentially a sign that one of the equation is redundant. because when we do the process, you notice that one equation is essentially the same as the previous one. And notice that sometimes it's not easier to spot in the beginning why one equation is redundant. If you look carefully, let's go back to the actual example. So if you look carefully here with the equations, notice that if I add, let's see, if I add the first and the third one, right? So I have 2x plus x is 3x, 5y minus 3y is 2y, 3z minus z is 2z. So if you notice right from the beginning that the sum of the two equations makes the second equation, we notice that then the second equation is basically nothing new. It's a combination of the previous ones. So this is really like having two equations with three unknowns, which, in this case, ended up having infinitely many solutions. You could still have an inconsistent system even if you have three equations. Even if you have only two equations and three unknowns, so all possibilities can happen in the end. But the point is, whether it's consistent, inconsistent, or whether you have a unique or infinitely many solutions, it may not be easy to see from the beginning. On the other hand, if you have fewer equations or fewer unknowns, inconsistency, sometimes it's easier to spot. So for example, let's say one equation, let's call this example 4. Let's say one equation is x minus y equals, or let's say 2x minus y equals 3, and then 4x minus 2y equals 7. So you might notice if you look carefully that the left side basically is twice the first side. So 2x minus y, 4x minus y is just double the left side. So this is the double of the left side of the first equation. On the other hand, the right-hand side is not double the first, right? 7 is not twice times 3. Now, if you don't spot that, again, you can proceed with the elimination. So let's say we want to eliminate y, which means I need to multiply by minus 2, the first equation. So I have minus 4x plus 2y equals minus 6. And then 4x minus 2y equals 7. And when we add the two, we get 0. So in fact, we eliminate both of them on the left side equals minus 6 plus 7, which is 1, which is of course not true. Therefore, the system is inconsistent. This is another hallmark that I want you to keep in mind when we move on to the Gaussian elimination, to the algorithm, which shows that the system is inconsistent. So if you have 0 on the left side of the equality and a non-zero value on the right, obviously that's not possible. So that means if we didn't make any computation mistake, it means that our system is inconsistent. And for the last part, we're going to do, like I said, another 3x3 system, but this time a consistent one. All right, so let's do an example this time with 3 equations and 3 unknowns. X minus y minus z equals 0, 2x plus 3y plus z equals 5, and x plus y minus z equals 2. So I make it easier than before a little bit in the sense that we don't need to multiply any coefficients to eliminate one unknown. Notice that z is the most convenient one. If you look at the coefficients of z, we can simply add second equation to the first and the third. And that accomplishes elimination of z. So pay attention here. If we add the first two, I get 3x plus 2y minus y plus 3y is 2 equals 5. Now, so that's first plus second. And then second plus the third gives me 3x plus 4y equals 7. So second equation plus the third. How do we eliminate further one variable? Well, again, the easiest thing is to multiply by minus 1, one of them, just to make the coefficients of x opposite to each other. So we get minus 3x minus 4y equals minus 7. add the two, 5 minus 7 is minus 2. That gives me y equals 1. So now we can just do back substitution for all the other variables. We go back to one of these two equations, replace y with the value that we found, 1. So 3x is 5 minus 2, which is 3. X is equal to 1. Then we're going to bring both these two values in one of the initial equations, plug them in. So 1 minus 1 plus z equals 0. That gives me z equals 0. So solutions, the unique solution in this case is 1, 1, 0. So in this case, the system is consistent and it has a unique solution. Okay, so for now, the homework, remember, do elimination. For practice, if you have time, try to do it in more than one way, because you can eliminate one variable or you choose a different variable, so there are many ways to do the same problem. And try to focus primarily on these convenient coefficients that you multiply each equation, because this is basically the most important mechanics of the Gaussian elimination. You look at the coefficients and you basically have a very systematic way of eliminating these variables. And we will do it in a much more efficient way, which leads us to the concept of a matrix, in fact, because the algorithm doesn't even write the equation in the traditional form. It will track only the coefficients, because that's all that matters in the case of linear systems. So that's it for today. I'll see you next time.